Good everyone, I am here to report Chapter 20, Design of Rigid Pavements. Rigid highway pavements are normally constructed of Portland cement, concrete, and may or may not have a base course between the subgrade and the concrete surface. Rigid pavements have some flexural strength that permits them to sustain a beam-like action across minor irregularities in underlying material. Thus, the minor irregularities may not be reflected in the concrete pavement. Properly designed and constructed rigid pavements have some service lives and usually are less expensive to maintain than flexible pavements. Thickness of heavy concrete pavements normally range from 6 to 13 inches. Different types of rigid pavements as described later in this chapter. These pavement types usually are constructed to carry heavy traffic loads, although they have been used for residential and local roads. In this topic, we cover the major aspect of rigid pavement design, sufficient for understanding of design principle of the basic types. Also in this topic covered include a description of the basic types of rigid pavements and the material used. A discussion also of the stresses imposed by traffic wheel loads and temperature differential on concrete pavement. Also, a description of AS2 or American Concrete Pavement Association design methods. And in addition of the above introduction is presented on the mechanistic empirical design method. Material used in rigid pavements. First, the Portland cement concrete used for rigid pavement design or Portland cement. Coarse aggregate, fine aggregate, and water. Steel reinforcing rods may or may not be used depending on the type of pavement being constructed. A description of the quality equipments for each of the basic materials is presented in the following section. Portland cement. First to be used in pavement. Portland cement is manufactured by crushing and pulverizing a carefully prepared mix of limestone, marl, and clay or shale, and by burning the mixture at the high temperature to the about 2,800 degree Fahrenheit to form a clicker. Clicker is then allowed to cool as a small quantity of gimsop is added, and the mixture is then ground until more than 90% of the material passes the number 200 seeds. The main chemical constituents of the material are tricalcium silicate, dicalcium silicate, and tetracalcium aluminum ferrite. The material is usually transported in 1 feet 3 bags which weighing 94 pounds, although it also be transported in bulk for large projects. There are a lot of agency, but most of highway agency use either the American Society for Testing Materials or ASTM specification, ASTM designations C150, or the American Association of State Highway and Transportation Official AS2 specification, AS2 designation M85 for specific Portland cement quality equipments used in their projects. There are 5 types of Portland in AH2. First type 1, is suitable for general concrete construction where no special properties are required. A manufacturer will supply this type of cement when no specific type is requested. For type 2, is suitable for use in general concrete construction where the concrete will be exposed to moderate action of sulfate or where moderate heat of hydration is required. And in type 3, is suitable for concrete construction that requires high concrete strength in a relatively short time. It is sometimes referred as a high early strength cement. Type 1A and Type 2A and Type 3A are similar to Type 1 to 3 respectively, but contain a small amount to 4 to 8% of total mix of entrapped air. This, this is achieved during a production by thoroughly mixing the cement with air entraining agents and grinding the mixtures. In third type of A and 2 are more resistant to calcium chloride and de-icing salts and are therefore more durable. In type 4 is suitable for projects where low heat of hydration is necessary, while the type 5 last type is used in concrete construction projects where the concrete will be exposed to high sulfate action. In the table 20, you will know the show the proportion of the chemicals constituents for each of the 5 cement. There's cement type A, na siya sa table 20. Next is the coarse aggregates. Next to be used in pavement. The coarse aggregates used in Portland cement concrete in inert materials that do not react with cement and usually are comprised for crushed gravel, stone, or blast furnace slag. The coarse aggregates may be any one of the three materials or else a combination of two or all three. One of the major requirements for core aggregates used in Portland cement concrete is the gradation of material. A material is well graded with a maximum size specified. Material retained in number 4 sieve is considered coarse aggregate. Coarse aggregate must be clean. This is achieved by specifying the maximum percentage of the deleterious substances allowed in the material. Other quality equipments include the ability of aggregates to resist abrasion and soundness of the aggregates. Fine aggregates. Sun is, sand is mainly used as the fine aggregate in Portland cement concrete. Specifications for this material usually include grading equipments, soundness, and cleanliness. Standard specification for the fine aggregate of Portland cement concrete as to designation M6 give grading requirements normally adopted by state highway agency. The, the soundness requirements is usually given in terms of the maximum permitted loss in the material after 5 alternate cycles for wetting and drying in the soundness test. A maximum of 10% weight loss is usually specified. So, mana ang chapter 20 na about sa graduation requirements for aggregates in Portland cement concrete or ASTM designation C33. Now next is water. The main water requirement stipulated is that the water used also should be suitable for drinking. Not salt water are not allowed. It must be suitable water that can be drink by people to be used in the cement. This requires that the quantity of organic matter, oil, acid, and alkalis should not be greater than the allowable amount in drinking water. Mani ang AAS to recommended particle size distribution for fine gauge used in Portland cement concrete. Reinforcing steel. Steel reinforcing may be used in concrete pavements to reduce the amount of cracking that occurs as a load transfer mechanism at joints or as means of tying two slabs together. Steel reinforcement used to control cracking is usually prepared to as a temperature steel, whereas steel rods use as load transfer mechanism are known as dowel bars, and those used to connect two slabs together as known as tie bars. Temperature steel. Temperature steel is provided in the form of a bar mat or a wire mesh consisting on a longitudinal and transverse steel wires welded at regular intervals. The mesh usually is placed about in 3 inch below the slab surface. The amount of steel required depends on the length of the pavement between expansion joints, the maximum stress desired in the concrete pavement, the thickness of the pavement, and the moduli of elasticity of the concrete and steel. With the following general guidelines for the minimum cross-sectional area of the temperature steel. First is cross-sectional area of longitudinal steel should not be at least equal to 0.1% of the cross-sectional area of the slab. Second is longitudinal wires should not less than number 2 gauge space at the maximum distance of 6 inch. Transverse wire should not be less than number 4 spaced at a maximum distance of 12 inch. Temperature steel does not prevent cracking of the slab, but it does control the crack widths because the steel acts as a tie holding the edges of the cracks together. Dual bars. Dual bars are used mainly as load transfer mechanism across joints. They provide flexural shearing and bearing resistance. The dual bars must be a much larger diameter than the bars used in temperature steel. Size section is based mainly in experience. Diameter of 1 to 11 over 2 inch and lengths of 2 to 3 feet have been used, with the bar usually spaced at 1 feet centers across the width of the slab. At least one end of the bar should be smooth and lubricated to facilitate free expansion. Tie bars are used to tie two sections of the pavements together, and therefore they should be either deformed bars or should contain hooks to facilitate the bonding of two sections of the concrete pavement with the bar. These bars are usually much smaller in diameter than the dual bars and are spaced of a larger center. Typically, diameter and spacing of these bars are 3/4 inch and 3 feet respectively. Joints in concrete pavements. Different types of joints are placed in concrete pavements to limit the stresses induced by temperature changes and to facilitate proper bonding of two adjacent sections of pavement when there is a time lapse between their construction. For example, between the end of one day's work and the beginning of the next. These joints can be divided into four basic categories. First is expansion joints, contraction joints, hinge joints, construction joints. Ex- Expansion joints is when concrete pavement is subjected to an increase in temperature. It will expand, resulting on increase of length of the slab. When the temperature is sufficient high, the slab will buckle or blow up if it is sufficiently long and if no provision is made to accommodate the increased length. Therefore, expansion joints are usually placed transversely at regular intervals to provide adequate space for the slab to expand. These joints are placed across the fall wide of the slab and are 3/4 to 1 inch wide in the longitudinal direction. They must create a distinct break through the dip of the slab, and the joint space is filled with compressible filler material that permits the slab to expand. Filler materials can be cork, rubber, bituminous materials, or bituminous fabrics. Our example for typical expansion joint on the top, and next is the typical contraction joint, and the third is the typical hinge joint. A means of transferring the loads across the joint space must be provided, since there's no aggregates that will develop an interlocking mechanism. The load transfer mechanism is usually a smooth dual bar that is lubricated on one side. Some states no longer use expansion joints because in the inability of the load transfer mechanism to adequately transfer the load. Other states continue to use expansion joints and even may use them in space of contraction joints. Contraction joints, when concrete pavement is subjected to a decrease in temperature, the slab will contract if it is free to move. Prevention of this contraction movement will induce tensile stresses in the concrete pavement. A typical contraction joint is shown in figure 22, 20.2 katong ganina na akong ipakita kauban ang hinge o ang expansion joint. This is the hinge joint. Are used mainly to reduce cracking along the center line of the heavy pavements. So muna sila sa ubos ang adyang porma sa hinge joints. Contraction joints are used transversely across the pavement to provide suitable transition between concrete laid at different times. Types of rigid highway pavements. Rigid highway pavements can be divided into three general types: plain concrete pavements, simply reinforced concrete pavements, and continuously reinforced concrete pavements. The definition of each pavement type is related to the amount of reinforcement used. Jointed plain concrete pavement, or GPCP, has no temperature steel or dowels for load transfer. However, steel bars often are used to provide a hinge effect of longitudinal joints and to prevent the opening of these joints. Plain concrete pavements are used mainly on low volume highways or when cement stabilized soils are used on subspace. Joints are placed relatively shortest distant to 10 to 20 feet than with other types of concrete pavements to reduce the amount of cracking. In some cases, the transverse joints of plain concrete pavements are skewed about 4 to 5 feet in plan, such that only one wheel of a vehicle passes through the joint at a time. Simply reinforced concrete bend. Pavements Concrete pavements have dowels for the transfer of traffic loads across joints with these joints spaced at a larger distance ranging from 30 to 100 feet. Temperature steel is used throughout the slab with the amount of dependent on the length of slab. Tie bars are used commonly on longitudinal joints. Continuously reinforced concrete pavement or CRCP have no transverse joints except construction joints or expansion joints when they are necessary at specific position, such as bridges. These pavements have a relatively high percentage of steel with a minimum usually of 0.6% of the cross section of slab. They also contain tie bars across the longitudinal joints. Pumping of rigid pavements is an important phenomenon associated with rigid pavements. Pumping is the discharge of water and subgrade or subbase material through joints, cracks, and along the pavement's edges. It primarily is caused by the repeated deflection of the pavement slab in the presence of accumulated water beneath it. The mechanism of pumping can best be explained by considering the consequence of events that lead to it. The first event is the formation of void present beneath the pavement. This void forms can from either be combination of plastic, the formation of the soil due to exposed loads, and the elastic rebound of the pavement after it has been deflected by the exposed load, or warping of the pavement, which occurs as a result of temperature gradient within the slab. Water then accumulates in the space after many repetition of traffic load. Further load repetition and application of the slab will result in slurry being ejected to the surface. Pumping action will be continued with the result that is relatively large void space is formed underneath the concrete slab. Visual manifestation of pumping include discharge of water from cracks and joints, spilling near the center line of the pavement at a transverse crack or joint, mud boils at the edge of the pavement surface discoloration caused by the subgrade soil, breaking of pavements at the corners. Design consideration for preventing pumping. A major design consideration for the preventing pumping is the reduction of elimination of expansion joints, since pumping is usually associated with these joints. Since pumping is also associated with fine-grained soil, another design considered is either to replace soils that are susceptible to pumping with a nominal. Stresses in rigid pavements. Stresses are developed in rigid pavements as a result of several factors, including the action of traffic load, the expansion and construction of the concrete due to temperature changes, yielding of the subspace of subgrade supporting the concrete pavement, and volumetric changes. For example, traffic wheel loads will induce flexible flexural stresses that are dependent on the location of the vehicle wheels related to the edge of the pavement, whereas expansion and contraction may induce tensile and compressive stresses. These different factors can be induced stresses in concrete pavement have made the theoretical determination of stresses after complex requirement. The following simplifying assumptions. First is concrete pavement slab as considered as unreinforced concrete beams. Any contribution made to the flexural strength by the inclusion of reinforcing steel is neglected. Second, the combination of flexural and direct tensile stresses will in- inevitably result in transverse and longitudinal cracks. The provision of suitable crack control in the form of joints, however, controls the occurrence of these cracks, thereby maintaining the beam action of the large sections of the pavement. Third is the supporting subbase and or subgrade layer acts as an elastic material in that it deflects as the application of the traffic load and recovers at the removal of the load. Stresses induced by bending. The ability of rigid pavements to sustain a beam-like action across irregularities in the underlying materials suggests that the theory of bending is fundamental to the analysis of stresses in such pavement. The theory of a beam-supported analytic foundation therefore can be used to analyze the stresses in the pavement when it's externally loaded. This is the deformation of beam on elastic foundation. A general relationship between the most of the radius of curvature of the beam is given as 1 over r equals to m over ei, where r is the radius of curvature, m is the moment of beam, e is the modulus of elasticity, and I is the moment of inertia. The general differential equation relating the moment of any section of the beam with a deflection in that section is given as m equals to ei over d squared times y over d times x squared. Whereas the basic differential equation for the deflection of an elastic foundation is given as ei times d to the fourth over d x to the fourth equals to my negative qy equals to q. The basic differential equation for a slab is given as mx equals to quantity of eh cube over 12 times open parenthesis 1 minus u squared close parenthesis as given as, where h is the thickness of slab, u is the Poisson ratio of concrete, w is deflection of the slab at a given point, mx is a bending moment at the point about the x-axis, my bending moment at a point about y-axis. The AL term in equation 2 is called the stiffness of the beam, whereas the stiffness of the slab is given by the term within the square brackets of E15. This term usually is denoted as D, where D is equal to E CH cube over 12 open parenthesis y minus u squared close parenthesis. In developing expression for stress in a concrete pavement, Westergaard made use the radius of relative stiffness, which depends on the stiffness of the slab, and the modulus of subgrade reaction of the soil. It is given as na kani mo ni siya ang formula where E is radius of relative stiffness, the sign is inches. E is the modulus of elasticity of the concrete pavements. Ang iyang sign is pounds per inch squared. H is equals to thickness of pavement inches. U is the Poisson ratio of the concrete pavements, and K is the modulus of subgrade reaction. It will be seen later that the radius of relative stiffness is important parameter in the equation used to determine various stresses in a concrete pavement. Stresses due to traffic wheel loads. The basic equation for determining flexural stresses in concrete pavements due to traffic wheel loads were first developed by Westergaard. Although several theoretical develops had been made since then, the Westergaard equations are still considered a fundamental tool for evaluating stresses on concrete pavements. Westergaard considered three theoretical locations of the wheel load on the concrete pavement. Sama na siya ang critical location of wheel loads in concrete pavements. Ano siya ang forma. So, developing of the equation. Their location shows and they described as follow. In the case 1, load is applied in the corner of the rectangular slab. This provides for the cases when the wheel load is applied in the intersection of the pavement edge and a transverse joint. Sama na ang class A or class 1. So next is class B. Load is applied at the interior of the slab at a considerable distance from its edges. Mana ang class B, ang class A di ay. Lastly is load is applied at the class C. Load is applied at the edge of the slab at a considerable distance away from the corner. So ladyo ra siya. Mana ang class case C. I mean case not class. Sorry guys. The location shown in case 1 to 3 figure are the critical location presently used for the relatively wide pavements now being constructed. During the night, however, the temperature at the bottom of the slab is higher than the surface, thereby revising the temperature gradient, which results in the tendency for the slab edges to curl upward. The equation for stresses due to traffic load reflect this phenomenon of concrete pavements. The original equation developed by Westergaard were modified using the result of full-scale tests conducted by the Bureau of Public Roads. This modified equation for a different loading condition as follows. First is edge loading. When the edge of the slab are warped upward at night. So, muna siya ang formula sa edge loading. Edge loading when the slab is upward or when the edge of the slab is curled downward. So, malagyan na siya. Palihara na sa kanina. The interior loading. So, muna siya ang formula which QE is maximum stress index in the bottom slab directly under the load P and applied at the edge and the direction parallel to the edge. Is I maximum tensile for stress index the bottom of the slab directly under the load P at the interior of the slab. So P is applied load in pounds, including allowance for impact. H is thickness of the slab. E is radius of relatively stiffness. Ang formula. E na dako is modulus of elasticity of concrete. U is the Poisson ratio of concrete. K is the Subgrade modulus B is the radius of equivalent distribution for pressure. And lastly is A, radius for contract area of load. So mana sadya ang for circular loaded area. So man is ang sample sa pagpangita og using Westergaard equation and using the Illuminates equation. Substitute. So nakakuha siya sa Westergaard equation na result is 61.07 pounds per inch squared. For the use of the Illuminates equation, kaog 92.9 pounds per inch squared. Stresses due to temperature effects. The tendency of the slab edges to cool downward during the day and upward during the night as a result of temperature gradients is resisted by the weight of the slab itself. Compressive and tensile stresses therefore are induced at the top of the bottom slab respectively during the day, whereas tensile stress are induced at the point and compressive stress at the bottom during the night. So mas dyan curling stresses fine. Mana si dyan where you the OX maximum curling stress in pounds per inch squared at the edge of the slab and the direction of the slab length due temperature difference between the top and the bottom of the slab. Next is the XI, which is the maximum curling stress at the interior of the slab in the direction of the slab length due to temperature difference between the top and the bottom of the slab. E is the modulus again of the elasticity of concrete. Here is the Poisson ratio of concrete. Cx and Cy coefficients that are depending on the radius of relative stiffness of the concrete and can be deducted from the following page. E is the thermal coefficient of expansion and contraction of concrete. And lastly, T is the temperature difference between the top and the bottom of the slab. So, mas dyan temperature changes, gikan sa 0, ming saka, ming maintain. So, considering the unit of pavements, the frictional force of developed due to a uniform drop of temperature is manay formula where gamay na F is coefficient of the friction between the bottom of concrete pavements and subgrade. H is thickness of concrete pavement. L is length for the pavement between contraction joints. And lastly is YC density of concrete. Muna sila ang mga formula sa laas na ang kibasa. And thank you guys for watching and sana unta na may makatunan. Thank you guys.